So before we jump on to calculating any other Laplace transformation, it is time for us to learn about some common properties. And these properties are very helpful for us to find out the Laplace transformation of functions without doing heavy integrals. Now, I must warn you beforehand is that a great deal of calculation might be mitigated by the application of these properties. However, it is not guaranteed that you'll find out the Laplace transformation of all functions by these properties. So here I will enlist 4 properties of Laplace transformation, and then along with showing those properties, I'll also show you the proof. Alright, so buckle up. So the first property I'm going to discuss about is the property of linearity. Okay, so this is how it goes. So let us find out the Laplace transformation of a linear combination of functions. So let's, for the sake of simplicity, take the linear combination of 2 functions. So we have a constant c1 and then a function f1 of t, and then we have c2 times another function capital F2 of t. So f1, f2 are functions of t, and c1 and c2 are constants. At least that's how linear combination goes. If we plug these into the definition, what do we find? Well, we should find 2 integrals. The first one being the integral from 0 to infinity a to the power negative st, and then we have c1 times f1 of t plus c2 f2 of t whole, well, I have to close the brackets, and then dt. Now, of course, the integration is a linear process, so we can break off this bracket and write down c1 and then integration from 0 to infinity e to the negative st f1 of t dt plus c2 and then integration from 0 to infinity e to the negative st and then f2 of t dt. What this shows us is that it is equal to c1 times the Laplace transformation of f1 of t plus c2 times the Laplace transformation of f2 of t. So basically, the Laplace transformation of a linear combination of functions should be equal to the linear combination of Laplace transformations of those functions. And that is how the Laplace transformation preserves the linearity. And of course, as you can assume, this property of linearity can be generalized pretty easily. The next property I'll be talking about is very simple, and it is the following. If we are given a particular Laplace transformation, or a particular Laplace transformation is known, so for example, the transformation of this function f of t is known to be small f of s, then we can immediately decide that the Laplace transformation of the function f multiplied by e to the power at this is going to be equal to that small function f of s, but this time it is shifted or been translated. That's why the name translation or shifting property by a. So small f of s minus a. And this is the second property, but it is called the first translation or shifting property. There are actually two shifting properties. This is the first one. Next one will be the second translation or shifting property. This property, as it turns out, is very easy to prove, and that's what I'm going to do. So basically what you do is the following. So you say, alright, notice if you have f of t and this is going to be equal to integration from 0 to infinity e to the power minus st as it is in the definition, and then f of t dt, and that is of course f of s. So basically you're defining what f of s means. It says this specific combination, and then whatever is in here is going to be put in here. So if we have s in here in the exponents multiplied with t, then of course here the argument will be s. Of course, if it is anything else, then the argument will just substitute that. So if we do have this function multiplied by e to the power a of t, where a is a number, then of course, as we can assume, everything is going to be the same. So we have integration of 0 to infinity e to the power negative st, but then we have this extra factor e to the power at f of t dt. If we organize it a little bit, that means if we bring the exponents together, we can really write it e to the power negative s minus a into t, and then f of t dt. It turns out it's exactly like the integral we have in here, except s has been substituted by s minus a. So this is simply f, but s is substituted by s minus a, which proves our statement. Okay, so this is the third property, which is called the second translation or second shifting property. And as before, we have a Laplace transformation of a given function, and then we have another function which, after a certain number, looks like this function right here, capital F of t, but it's been shifted. So remember, in the previous one, the result was shifted. The result in the S space was shifted by A. In here, the function or the argument or the input is shifted. And how does it translate to the result? Well, that's the interesting part. So if this is the case, then the Laplace transformation of this shifted function, so therefore we write Laplace transformation of g of t is equal to e to the power negative as times f of s. Isn't that interesting? So shifting in one takes this factor, this exponential factor, multiplied to the other. So it has sort of an interesting symmetry, but that's of course a property hidden on the plane side, and we intend to use it in our advantage. So as a proof, we have this definition. So the Laplace transformation of g of t is equal to the integration from 0 to infinity e to the power negative st, and then g of t dt. That's all fine, that's by definition, there is nothing new. But if we do look at the definition of g of t, we notice that when t is smaller than a, then the function g of t is 0. So from 0 to a, this function g of t does not contribute anything to its Laplace transform. It's only the part from a to infinity that contributes dominantly. In fact, the only contribution comes from that part. So what we find is basically this is equivalent of writing a to infinity, because from 0 to a, that part is just simply 0, and the integration over 0, well, it is 0. So what do we find? We find e to the power negative st, and then f of t minus a dt. Now, of course, we can turn this into our familiar form of Laplace integral by taking a change in variable. So basically, we define t minus a equals u, and then what we get is t equals u plus a. Now, if we take dt, all right, we get that is equal to du. So we can substitute everything in this integral right here, only to find that instead of dt we have du, instead of f of t minus a we have f of u, and then instead of e to the power negative st we have e to the power negative s times, well, what do we find? We find u or plus a. Alright, so that's where we have substituted t. And u, of course, runs from 0 to infinity, unlike t, which runs from a to infinity. And this is the integration for Laplace transform, except the dummy variable has changed. Well, the dummy variable is the dummy variable. It doesn't matter what the actual variable is, because after a sum, the index always goes away, and after an integration, dummy variable always goes away. So what we can do now is to take e to the power negative sa, because that whole part is constant, and take it out of the integral. So we find e to the power negative sa, and then from 0 to infinity we have e to the power negative su, f of u, du, and that gives us e to the power negative sa, and then f of s, which really proves our assertion or the statement of the property. Finally, as the fourth property, we enlist the one called the change of scale. So what we basically do is, by taking f of t and scaling its argument by a factor, in this case we have called this factor as a, we want to see what is the change induced in the corresponding Laplace transformation. As it turns out, the Laplace transformation of f of at is equal to 1 over, so there's a factor that comes out, and then we have f of s over a, so we see s is also getting scaled, but really in the opposite fashion as t is getting scaled. So this is actually an important property, and we should strive to prove it right now. So the proof is very simple. What we do is we take L of f of at, and as before and as always we substitute it into the definition. So we have e to the power negative st f of at dt. And just like the previous one, what we do is we define a new variable, which is u, and we say u is equal to at, and so therefore t is going to be u divided by a. If I take dt, that would be du over a. If we substitute these things in here, what we get is, well, as t gets to 0, u also gets to 0, and as t gets to infinity, u also gets to infinity. So the limits remains the same, so we still have 0 to infinity, but then we have negative s divided by, we have su divided by a. Of course, I can write it as s divided by a into u, and that's what I was initially going with. And then I have f of u, and then I have du over a. So I can rewrite this, and then I get 1 over a, and then the integration from 0 to infinity e to the power negative s divided by a times u f of u du. Well, this thing here is simply f of s divided by a, because this factor s is accompanied by 1 over a. So altogether we have 1 over a and then f of s over a, which proves our statement of the property.